So yeah, by now you should be pretty familiar with this little Genie18 project board. Useful little bit of kit. We're now going to talk about physical output. So we've done indicator LEDs, we've looked a little bit without actually covering it in a lot of detail. We've talked about this alphanumeric LCD. But we're now going to go on to slightly more useful outputs like motors, solenoids, physical electromechanical outputs. So we'll start off little solenoid like that. This kind of thing, dinky little thing. It doesn't need a lot of power, so we can run it straight off these Q outputs, no problem. Small DC motors as well, no problem. You can run these kind of size DC motors without a problem on these outputs here. When you start getting bigger than this size DC motor, you might run into trouble. It might just use more power than this can deliver. So you might want to think about either amplifying it or using a bigger circuit. So we can talk about higher power transistors, or we can use one of these devices here. Now this is very similar to a solenoid. It's an electromagnetic coil which energizes a bigger switch, so you can switch on a much bigger circuit with one of these things, and that's called a relay. So solenoids and relays I'm going to be covering in a couple of episodes time. They're really useful and they're no problem running off a Genie18 project board like this. I mentioned bigger DC motors, but another issue with this, it isn't very easy to run these in reverse. So you've got one direction here, you send an output as high, it opens this gates and drains it down to 0 volts, switching this motor on. What if you want to run it in reverse? Well, here we use an arrangement of 4 transistors called an H-bridge. Now an H-bridge is a complicated thing, and it looks a little bit like this, where you can see the transistors will open in opposite direction. So you imagine the S shape going one way when those 2 transistors are opened. Switched on, it will allow the current to go that direction, and then if the other output switches the other transistors on, you can see those 2 transistors will open, the current goes in the opposite direction, and the motor will spin the other way round. So that, in a nutshell, is an H-bridge, and it can be quite a tricky thing to wire up on a breadboard using 4 little transistors. Notice also we've got PNP and NPN transistors as well, so they've got to be all wired up the right way around. It's a little bit above and beyond what's needed for A-level design engineering, and if you're a novice electronics person, you might be more interested in this. Now you don't even have to use a specific motorboard like this Genie18 motorboard. It's more this chip that's interesting. It's called an L293D, and it's actually got built-in H-bridge built into it. It's 2 H-bridges in fact. So here we've got 4 outputs. Now they pair up to being 2 outputs for 2 DC motors, so you can have one on each like that. Now, because you can switch the polarity, and certainly in Circuit Wizard, it's easy to say, okay, output 1's on for it to go forward, or output 2's on for it to go backwards, as you can see with this interface here. It's nice and easy, and it just takes a headache out of working out how to use H-bridges. So that's really good. You can run 2 DC motors on one of these. You can also run certain types of stepper motor. Now I say certain types because you've got to be careful which type you're talking about. This is quite a common type that comes along with Arduino kits, and it's called a unipolar stepper motor. It's got 5 wires on it. Some have got more than 5 wires even, but it's not very easy to wire up with this thing. I tend to recommend a bipolar stepper motor. So here's one. It's a nice ideal one, this size. This is a 5-volt stepper motor, and to be honest, if you spot the colour coding where you've got yellow, orange, brown and black, that's normally a given. It's a good indication that this is going to be suitable. Little 5-volt stepper like that. I've got exactly the same type of stepper that works on the same principles. This one came out of an Epson printer. So these are really easy to find because how many dead Epson printers are there out on the street. And they all use these EM553 steppers. They're quite neat little steppers. They're very thin, so they're low profile, given their power as well. They're pretty good. And they're already geared, so it's quite a neat way of just kind of prototyping, coming up with a design like that. So these steppers use these 2 pairs of outputs, these 4 outputs, and being bipolar and having an H bridge on it, so an L293D, means that the polarity gets reversed, which is why it needs one less wire than this unipolar one. Now, as well as these little ones, you can also run bigger stepper motors. These are 12 volt steppers, and this one is a very common type called a NEMA 17. It's also a 4-wire bipolar stepper, but being 12 volts, this actually does run up to 12 volts. You notice it's got 6 to 12 volts there. However, I find that these actually draw too much current. I think the limit on this is 2 amps. These are 2 amps, and it just gets a little bit too hot and then starts missing steps. I would also say I've experimented using a 1 amp stepper like this one, 12 volt stepper, and it seems to work better, but again, after a minute or so, this gets too hot and it just starts missing steps. So I would recommend, if you're going to just play around with stepper control and you just want to kind of scale down your design and just say it would be a bigger stepper in real life, use a little 5 volt one with these colour plugs to it. So as well as steppers, you can have precision control with a servo as well. Now this works in a slightly different way. We've got 3 wires on this. You've got plus volt with red, brown is 0 volts, and then orange is the signal volts. So it's exactly the same output as an LED, and these plug into these unamplified things here. Now this motorboard is particularly useful because you've got let's get it the right way around. Yep, you've got 3 rows of 3 pins like that, so you can plug 3 servos up simultaneously without having to hack it at all or do anything complicated. So it's a neat way of using 3 different outputs, unamplified outputs, to control the angle on one of these things. Now again, I'll cover this in its own specific video, but these work in a slightly different way to steppers and DC motors. But steppers and servos are much better than DC motors when it comes to precision control, unless you use something like a rotary encoder, as we've covered in the first instance. So yeah, outputs, there you go. And like I say, with the servos, I just drop in the LCD as well, just because that uses the same interface, although this is really easy to use, so hopefully you'll have figured out how to use this already in the videos if you've been watching them in sequence. So there you have it. Right then, let's have a look at DC motors in a little more detail. So here I've got a proof of concept for a pet feeder door actuation. Now I've got a tiny little DC motor, geared DC motor here, and I'm using a motorboard because I want to run this in forwards and reverse so the door opens and closes. You'll see just in there, just turn it around, you can see it's geared once more onto this hinged door. And over on this side I've got 2 feedback loops. So I've got 2 digital switches here that just say when the door's open or closed. Now when a 3rd switch here, when I push it, it'll run. So what happens there, it goes in one direction, switch shuts, and then it pauses for a second and goes in the other direction till the other switch shuts. Now the good thing about using a feedback loop like that, using a feedback switch, it could even be an optical sensor or a rotary encoder, so you could count the number of revolutions it has before it comes to a standstill. It's better doing that than just timing how long the motor's on, just in case someone accidentally nudges it open like that. So it's going to open past its bottoming out, and that might damage the motor or break some teeth or something else. So it's always a good idea to have some form of feedback. Now if you look on the flowchart, you'll notice, so D2 is the actuation button, and then we've got motor in one direction, so the high output is coming out on output 6, and it's at full speed like that, so it's going up fast. Now the top actuation is down here, and this is actually a slightly better design than that one, just because this is round and it is able to carry on past the motor, so it's not going to damage anything as it comes to a standstill if it decelerates, if there's any inertia. And then it's got a 250 millisecond pause, and then we tell the motor to stop. So in other words, it overshoots that, just so that we know it's fully shut like that. Because that quarter of a second pause will just allow it to go a bit further. And then the command says neither 6 or 7 are on. So motor's stopped. Wait 1 second so the door's open. And then output 7 is on, so it goes backwards. And you don't actually switch it on and off here. You just use the slider. So what's happening here in terms of motor speed, it's not supplying less voltage to the output. What's happening here is a pulse width modulation. We cover a little bit in servos as well, but it's a similar kind of thing. So you'll find this in dimmer switches, for example. Certain kinds of LEDs are happy to have this kind of dimming. Rather than supplying less voltage, we just supply the full voltage for less time. So fully on is going to be consistent like that. It's just going to be on the whole time. A quarter on, in this case, is only a quarter of the time it's on, and then 0%, there's nothing there really, it's just a blip. So yeah, you can see you can adjust the power, the total motor power, just by the pulses, the amount of steps that it gets supplied with voltage, and that's what's happening here. So we can control the speed. I haven't in this example. And then obviously D1 off, as the motor comes back down, we're just going to push that button there as it comes to a standstill like that. So you might want to consider an optical switch. Less mechanical parts mean less likely to fail and wear out, so optical switches are good if you just had a hole in a sensor. It can be more expensive, but the little sensor that we use in the quadrature rotation sensor, that is fairly cheap, and it's a standalone product. And you can just straddle either side of this, and there could be a hole so that you can see what happens. But yeah, as you can see, DC motors are pretty easy to use in terms of motor control when you use one of these, for sure. And they can be easy to use on a PIC 18 if you don't need to go in reverse as well, if they're a little DC motor as well. So yeah, that is a nice little example of a DC motor.